This video is part 2 of the CFA video that demonstrates how to use STATA 14 to conduct a confirmatory factor analysis. And just to review, for this example, we use data from the Holzinger and Swineford research study that was done in 1939. In that study, they collected visual spatial data indicators, for example, tasks involving hands-on visual activities and manipulating cubes. These 3 subtests or indicators were used to form a spatial ability construct, and then they collected data from 3 verbal subtests, paragraph completion, sentence reading, word meaning, to form a verbal construct. And the idea is to test to see how well this model would fit in a larger population. And so what I wanted to do is show the concordance between the coefficients that are reported on the path diagram and those that are reported on the STATA output. And so I'm going to toggle to that output and just show you what the correspondence is so that you can get an idea of when you read this. Notice that the path from visual perceptual to the spatial construct, that coefficient is 0.77 or 0.78 if we round off, and you can see that is represented by this path coefficient here. Likewise, we have cubes being the path from cubes to spatial, or spatial to cubes, I'm sorry, is 0.43, and you can see that path coefficient there. And so you just go down and you can see how the coefficients for the paths, for the indicator variables for each of the constructs are located on this part of the output. Also, notice that these are the standard errors that are associated with each of these path coefficients, and these are the significance levels. And as we go down to this part of the output, these are the error variances that are associated with each one of the indicator variables. So for example, the error for visual perceptual is 0.39. And this is a little bit difficult to see here, but that's what's associated with this error. But if I click on that, I can see that the error variance here is 0.39, which corresponds to this error variance here. It's the same way with cubes. I can click on the error and see that the error variance is 0.81, which is fairly high. Same way with the other ones. And then the other statistics that's important for us to look at is the covariance, or the correlation between verbal and spatial. And this covariance is 0.46, and you can see that also as well on the output. So it's like a correlation between these 2 constructs that are consist of visual spatial types of tasks and verbal tasks. Then the other thing that we like to do, and I did present this in the last video, is that we like to see what the overall model fit would be for this particular configuration. And so if we go to statistics and we go to SEM, we can go to goodness of fit, and we want the overall goodness of fit for this particular activity. And so I can, and you'll notice that that's highlighted in blue. And I have different choices, but what I usually do is just click all and then OK. And you can see that now I have the chi-square values, and the chi-square values are were traditionally used to test how well a model fit was. But we also know from research that's been done over the years that the chi-square value is very sensitive to large sample sizes, and so we really want the chi-square value to not be significant, but in this case it is. And what has been done in the recently is that we've used the root mean square error of approximation as our gold standard, if you will, in terms of interpreting model fit. And the RMSEA for this particular analysis is 0.082, which doesn't indicate a perfect fit, but the fit is acceptable in terms of what researchers with CFA and structural equation modeling analysis would say. And then, of course, we have other types of ways to check how well the model fit is. And basically what the RMSEA is telling us is how well our sample and those parameter estimates, how well they fit estimates to an entire population. And again, this would be an adequate fit, fit that is a good fit would be 0.05 or less.